Hi, folks, and welcome to Solving Radical Equations. This is lesson 3.4, day 1. Tomorrow we're going to continue this idea, but today I think you're going to be okay to start it off without me. Sorry, I can't be there. Before we talk about solving radical equations, let's remind ourselves of some of the words that we've been using this whole time. For instance, the number that's under the radical symbol, we call that the radicand. So that's what we refer to when we see the word radicand. And this number that's floating outside of the radical symbol, we call that the index. That tells us what kind of root we are taking. Let's see if I can get that pen to work just a little bit better. The index there. For our work today, we're only going to be focusing on square roots, but in the future we may look at some other indices. So, to solve an equation that involves a variable in the radicand, so this is going to be a little bit different here from our other equation solving, what we need to do is we need to get the radicand on one side of the equation all alone in order to solve. So it's very similar to our earlier equation solving processes where we want to get the variable by itself. Before we do that, though, when we're involving radicals, we should focus on the radical and the radicand to help us get to where we need to be. So let's look at example 1 together. The square root of x minus 1 minus 9 equals 0. So if our goal is to isolate the variable eventually, and we need to isolate the radical first. So those inverse operations that you know and love, they're still going to stick around for a little while longer. So I'm going to add 9 to both sides. That makes the square root of x minus 1 equal to 9. Now that x is kind of locked inside that square root, but we know the key. We know that we can undo any square root by squaring. And if I square one side, I have to square the other side. So what happens? Well, that process of squaring makes that radical disappear completely. And all that's left is that radicand, x minus 1, on the left-hand side. On the right-hand side, 9 squared, that's an old friend, 81. So from here, x minus 1 equals 81. Well, okay then, we can solve this. We add 1 to both sides. We get x is equal to 82. Sounds pretty good. But you know me, we should always be checking our work, especially when we're solving equations, especially when we're solving a new equation type for the first time. So I'm going to check my work here. I'm going to go back to my original equation, which was the square root of x minus 1 minus 9 is equal to 0. And I'm going to replace that x with 82. Everything else stays exactly the same. So 82 minus 1 minus 9 is equal to 0. And let's keep simplifying there just a little bit. That would be that the square root of 81 minus 9 is equal to 0. And the square root of 81 is, in fact, 9. So we're going to get a statement, 0 equals 0. That is true. We're happy about that because our solution, x equals 82, is perfect. So some similarities here. Remember, we're trying to isolate the variable. We're using inverse operations to do that, and we are checking our work. So let's take a look at example 2. Example 2 says the square root of 2x minus 1 plus 5 is equal to 2. So once again, before we can isolate the variable, we have to isolate the radical itself. So let's start by subtracting 5 from both sides. That's going to leave the square root of 2x minus 1 is equal to negative 3. And we need to undo that radical, break that radicand out, and we're going to do that by squaring both sides. So on the left-hand side, all we have left is 2x minus 1, and on the right-hand side, remember when you're squaring a negative, it becomes positive. Check those parentheses in your calculator. So negative 3 times negative 3 gives us 9. So 2x minus 1 is equal to 9. All right. Let's add 1 to both sides. We get 2x is equal to 10. And with a little bit of division, dividing both sides by 2, we get x equals 5. So pretty straightforward, x equals 5, but again, we need to check. So we're checking, we're going all the way back to that original equation, which was 2x minus 1 plus 5 outside the radical is equal to 2. And that 5 is going right in place of x. So this will be the square root of 2 times 5 minus 1, still under the radical, plus 5. We're checking, does that all equal to 2? So 2 times 5 is 10. This is the square root of 10 minus 1. And 10 minus 1 is 9, so this is the square root of 9. And the square root of 9 is 3, so we get the statement 3 plus 5 is equal to 2. AKA 8 is equal to 2. So I don't know about you, but I'm not sure that 8 is equal to 2. So what does that mean? Does that mean that x equals 5 isn't a solution? How can that be? We did the work, we solved, we isolated the variable, all of our inverse operations looked pretty appropriate there, and still somehow we got a number that wasn't a variable. This is something that's different about radical equations than other equations we've seen before. It is possible to get solutions that are not actual solutions to the equation. So my word of warning here is that all solutions, every single solution you get, whether it's 1 or 2 or more than that, must absolutely, definitely be checked back in the original equation. Because not all solutions will actually work. And we have a name for those. Any solution that results, in false statements when we substitute them back in, so like that 8 equals 2 is a false statement, are called extraneous. That's extraneous, extraneous solutions. And if that reminds you of the word extra, it should. So the long story short is it's possible to get extra solutions that aren't actual solutions. And so you might be asking yourself, how? How can that happen? Why is that a thing? The long story short, and if this answer doesn't quite satisfy you, I encourage you to check out some online resources and forums. There's a lot of discussion on this. But the long story short is that we're doing some operations here that are not necessarily reversible. So for instance, we can start with the equation x equals -1. Pretty straightforward, right? X equals -1. Sure. If we manipulate it a little bit, if we square both sides, that's totally legal. We would get something that says x squared is equal to 1. Great, that's true. Great. If we were to take this and go in reverse, take that x squared is equal to 1 and take the square root of both sides, right, essentially undoing that square, we're going to get two answers. We're going to get x is equal to 1 and x is equal to -1. However, if I think back to my original equation, x is equal to -1, only one of these actually works. So this is where the idea of an extraneous solution comes from, is the operations that we're doing while we say that they undo one another, The idea of reversibility is not exactly the same here as it is with our other operations, addition, subtraction, multiplication, and division. So as we do this, every single solution has to be checked. We're going to do these next examples together. If you're watching this on your own, you're welcome to pause and work through the example and then come back and double check with me. If you're watching this with the whole class, you're of course welcome to work at your own pace, but here we go. So example 3 says square root of 1 plus x squared is equal to 5. Just like in earlier examples, I need to undo that square, or I need to get the 1 plus x squared out of the radicand. So I'm going to square both sides. That leaves me with a simple 1 plus x squared on the left-hand side, and on the right-hand side, 5 squared is 25. So going to subtract 1 from both sides. That's great. I'm going to get x squared is equal to 24. And my goal is to get x, not x squared. So I do have to square root. Feels kind of funny because we squared and then now we're square rooting again, but that's life. So we get x is equal to plus or minus the square root of 24. Remember, every number has 2 square roots. If you really enjoyed simplifying radicals, you could simplify this as plus or minus 2 root 6. Be a total blast there. But either way, we have to check this. We have 2 solutions now to check. So we're going to check, and that's a little bit much purple. I'm going to tone that back just a little bit. We're going to check x equals the square root of 24, and we're going to check x equals the negative square root of 24. So to do that, again, back to our original. So our original was the square root of 1 plus x squared is equal to 5. So if I substitute the positive square root of 24 in there, the square root of 24 squared is going to give me 24. So my radicand will be 1 plus 24. And 1 plus 24 is, of course, 25. And when I completely evaluate this, I get a true statement. 5 is, in fact, equal to 5. So that's good. We have at least one solution that works. Let's double check and verify our second equation and make sure it's not extraneous. So taking the square root of 1 plus, and now I'm doing the negative square root of 24 squared. Say that 10 times fast. But when I square a negative number, it comes out positive because it's negative times a negative. So this is 1 plus 24. And so this starts to look pretty similar to what I did before. This is the square root of 25 now, and the square root of 25 is 5. So this time we actually get 2 solutions that are going to hold up here, that are going to work. Plus or minus the square root of 24, or plus or minus 2 root 6, depending on how fancy you feel with your simplifying. So make sure we're checking every solution. In this case, we had 2 solutions to check, but it wasn't so bad. Example 4. Ooh, this time we've got 2 radicals, 2 radicands, and nothing's really moving in and out of those radicals. We can't combine square roots through addition or subtraction, but we can break square roots using squaring. So that's where we're going to start. So with both of these, once we apply that square, we're left with just the radicand. So we're left with 2x minus 1 is equal to x plus 1. And you've solved equations like this hundreds of times before. There's lots of different first steps you could take. I'm going to subtract x from both sides first. And I'm going to get x minus 1 is equal to 1. And once I add 1 to both sides, I'm going to get x is equal to 2. Now, that was really nice. It felt like I was just solving any old equation from back in the day, but I still have to check. So that's what I'm going to do. I'm going to check that x equals 2 really works. So my original was 2x minus 1. Sorry, the square root of 2x minus 1 is equal to the square root of x plus 1. So 2 times 2 and 2 plus 1 when I replace x with 2. So that gives me the square root of 4 minus 1 on the left-hand side and the square root of 3 on the right-hand side. I could simplify 4 minus 1 to 3, and I get a true statement. The square root of 3 is equal to the square root of 3. So our solution here totally works out. So I'm going to hold it here for just a couple of seconds to make a couple of reminders. That square root, we really can't move anything in or out of it, despite the fact that in example 4 we had 2 square roots. We had the same index on both sides. Our best plan of action is to undo that square root by squaring. Example 5 and example 6 are a little bit different than the previous ones. While example 4 did have variables on both sides of the equation, examples 5 and 6 have variables on both sides of the equations, and they're not all under a radical, which means that this is going to start to look a little bit different once we apply that initial strategy, which we do have to apply. We can't work with that square root. We need to start by squaring some things. So we square the left-hand side, we're left with 2x minus 4. On the right-hand side, though, we've seen stuff like this before. When we're squaring x minus 2, that's really x minus 2 times x minus 2. It's not just squaring both x and 2. If we were to evaluate that by multiplication, on the right-hand side, we'd get x squared minus 4x plus 4. And this equation right now should spark little jog down memory lane, throwback Thursday, if you will, to quadratics. We spent a lot of time solving quadratics, and I hope we haven't forgotten those skills, because right now we have a quadratic equation. We were solving a radical equation, and when we transformed it, now it's a quadratic equation. But I don't believe we've totally forgotten that. We remember we have to have one side completely set equal to 0. So I'm going to achieve that by subtracting 2x from both sides. And in one step here, I'm also going to add 4 to both sides so that that left-hand side is exactly just 0. And on the right-hand side, I get x squared minus 6x plus 8. So just as a reminder, we have several different strategies for solving quadratic equations. We could factor, or we could use the quadratic formula if we needed to. That quadratic formula is still a good friend of ours. In this case, I'm going to use factoring. I'm not going to go through the factoring process here, but if once that's all done, I end up with x minus 4 times x minus 2. And this, we've done this 100 times. We've set each one of those factors equal to 0. So in the end, we get the solutions x equals positive 4 and x equals positive 2. Now, all that work was pretty great, right? We did some quadratics, we did some factoring. It was amazing, but these are still radical functions. So unfortunately, we're just not quite done yet. We need to check both solutions. So I'm going to check x equals 4, and I'm also going to check x equals 2. And I'm going to have to use my original equation. I want to use the unaltered version before I've done any operations to it. So remember, not all of those operations are reversible. So I'm going to replace x with 4, so that's the square root of 2 times 4 minus 4. And I'm wondering, is that equal to 4 minus 2? So I'm going to keep simplifying here. That left-hand side will be the square root of 8 minus 4. The right-hand side will be 2. The left-hand side, 8 minus 4, makes 4 in the radicand. And the square root of 4 is, in fact, 2. So we have a solution. X equals 4 totally works. If you're hearing any noise in the background, that's probably the pets there making a little bit of noise for your entertainment. So lucky all of us. Let's check x equals 2 while we're here. Replacing x with 2 in both halves of the equation, and on the right-hand side, that's 2 minus 2. So simplifying, we've got 4 minus 4 in the radicand and 0 on the right-hand side. 4 minus 4 is 0. And the square root of 0 is magically, wonderfully 0. I think we're glad to see that because all that hard work paid off. We have two solutions that actually hold up under scrutiny here. So our two solutions here are x equals 4 and x equals 2. Last example together before you start to do some examples on your own on your practice assignment. Example 6 is going to look really similar to example 5, but I think the practice is helpful. So starting by squaring both sides because of that square root, and when we square that left-hand side, we're going to get x squared minus 6x plus 9. Remember, you can use double distribution or the box method if we need a reminder there. And on the left-hand side, our radicand, negative 2x plus 30. So once again, this is a quadratic equation now. We have to apply those quadratic strategies, getting one side set equal to 0. So I'm going to use my inverse operations there, adding 2x to both sides and subtracting 30 from both sides. And when I clean that up a little bit, I get x squared minus 4x minus 21 is all equal to 0. Once again, if I'm comfortable with factoring, I think that's a very efficient way to do this. If I'm a little shaky on factoring, I've got the quadratic formula that I can also use here to solve this. When we factor, we would end up with x minus 7 and x plus 4 is equal to 0. And so setting both of those equal to 0, we'd end up with x equals 7 and x equals negative 4. So once again, we get two solutions to check here. That's not too surprising since we ended up with a quadratic, and we know that quadratics have two solutions. Just again means we have two things to check. So I'm going to check x equals 7, and I'm going to check x equals negative 4. Back in my original equation, which I'm just going to jot down really quickly for reference, x minus 3 is equal to the square root of negative 2x plus 30. So just a little reminder of what that original was. Let's check 7 first. When I replace x with 7, that's going to be 7 minus 3 on the left-hand side, and the square root of negative 2 times 7 plus 30 under that radical symbol. A little bit of algebra here. Is it arithmetic? I guess it's just arithmetic. Negative 14 plus 30 makes a whopping 16. And the square root of 16, ooh, we get 4 is equal to 4. Heck yes. It's beautiful. X equals 7 is definitely a solution. One more thing to check before we go. That's x equals negative 4. So that's negative 4. Oops, wrong color. Negative 4 minus 3. Said it was the last one, and apparently it's going to go a little bit weirdly. Okay, let's try that again. Negative 4 minus 3 is equal to the square root of negative 2 times negative 4 plus 30, and this is what we're checking. So on the left-hand side, see. Did I make a mistake earlier? I did. my factorization wasn't quite right there. When I have minus 4x right there, I want -7 and positive 3. So let me adjust that really quickly. This should be plus 3. And so that would change my solution to -3. And that's what I'm going to check. My apologies. So -3 there. All right, -3 minus 3. And let's see here. What was I doing? Oh, replacing that with -3. There we go. So -3 minus 3 is -6. And we have -2 times -3 is 6 plus 30. So -6 is equal to the square root of 36. Now the problem here is that we get kind of two possible outcomes. Square root of 36 is equal to 6 or -6. This doesn't really hold up here. So we've talked about using the positive square roots while we're working through simplifying radicals. And the same thing applies here. We're talking about taking positive square roots. And unfortunately, this is a negative. So we actually can't consider x equals -3 a solution. It is an extraneous solution. Other examples are probably going to be more outright, obviously inconsistent and showing that it's not a true solution. But just keep in mind that just because one solution works doesn't mean the other will. In this case, we only have one solution, x equals 7. So that would be a really good introduction to solving radical equations. So I encourage you to go over and take a look at that practice assignment for the remainder of the period. It's not technically due until the end of the period tomorrow, but that's so that we have enough time to ask and answer any questions that might pop up. Help one another out, answer each other's questions, be on task, and come in prepared tomorrow. Thanks for listening, and I will see you then.